Let's learn how to solve static equilibrium problems. These are some of the forces you should know. We've gone over this list before, so you should be very familiar with this list, so you should know all these forces. So static equilibrium. An object is in equilibrium if the sum of the forces on the object add up to 0. So in one dimension, Newton's second law would read like that. All the forces would equal 0. In two dimensions, we would say all the forces in the horizontal equal 0 and all the forces in the vertical equal 0. In addition, we would say that an object is in static equilibrium if the velocity is 0. So this is for objects that are not moving at all. So, working second law problems. Here are the steps that you should be familiar with. You need to identify the system being accelerated, define the coordinate system, be able to identify the forces by drawing a force diagram or free body diagram, include a motion map, draw a component diagram if necessary, and rotate the axis if necessary. You should be able to explicitly write out the sum of the forces equals mass times acceleration, which is Newton's second law. Then you should replace the actual forces in your free body diagram with the forces from, well, you should replace the forces in this equation with the actual forces from your free body diagram. If necessary, write Newton's second law in both the horizontal and vertical directions. Then substitute the numeric values where appropriate and solve for the unknowns. So here's an example of static equilibrium. It's a block that's not moving, and in this problem, we're being asked to find the weight of the block, find the force that the surface applies to the block, many times called the normal force, and find the force of friction. So there's a block. It's a 30 kilogram block sitting on an incline of 37 degrees. First, we need to identify the system that's being accelerated. It is indeed the block. Now, this is really important because in the equation, where the sum of the forces equals mass times acceleration, the block refers to the mass and acceleration value. So the block refers to both the mass and the acceleration in that part of Newton's second law. Then we need to define the coordinate system. That's the coordinate system. Up and to the right is positive because it's a little bit off axis there, and down to the right will be positive. That will be our coordinate system. Then we're going to identify the forces by drawing a force diagram. So we've got the normal force up and to the right. That's the force that the surface is pushing up onto the block. Then we got static friction in this direction. And then finally, the force due to gravity straight down. We need to include a motion map. And we notice that the velocity and acceleration are equal to 0. Therefore, the object's in static equilibrium. We're going to rotate the axes. And the reason we rotate the axes is this. If you look at our original force diagram, there are two forces off axis, the normal force and the static frictional force. Well, it will make our life a lot easier if we rotate it so that the normal force is pointing straight up and the static frictional force is pointing directly to the left. That leaves us only one force that's off axis. Then we have to draw our component diagram. We choose a force that's off axis, the force due to gravity, it's the only one that's off axis, and we draw both the horizontal and vertical components. My preference is to go directly down first with FGY and then go across with FGX. The reason I like that is because this angle becomes the incline angle. That angle there becomes 37 degrees. You need to convince yourself of that by doing a geometric proof. Then in this static equilibrium problem, let's look at the next step. Let's explicitly write out Newton's second law. Remember, you get credit just for doing that. Then we replace the forces in Newton's second law with the actual forces in our free body diagram. We're going to do that both in the horizontal and vertical directions. In the horizontal, let's look at what forces there are. I color-coded them so that we can tell that these are the two horizontal forces. Here is Newton's second law written out in the horizontal. Let's add up the forces that are in the horizontal. They're Fgx and Fs. That's what Newton's second law says to do. Add them up and set them equal to mass times acceleration. But this acceleration is just in the horizontal direction. Then in the vertical, we do the same thing where we write out Newton's second law, but we fill out this part of it, just like we did with the horizontal, with the vertical forces. In this case, the only vertical forces are the ones marked in red, the normal force, which is straight up, and Fgy, which is straight down. And that equals the mass times the acceleration in the vertical direction. Our next step is to look very closely at this right triangle. It's very important because we need to find both Fgx and Fgy. Before we can do that, we need to solve for the value of Fg. We know that Fg, the weight or the force due to gravity, is equal to mg, and that's the mass of 30 kilograms times 9.8 meters per second squared. Notice we're not using the negative sign for several reasons. The main reason is that we've tilted the axes and the force due to gravity is not pointing straight down now. We do have its direction. It's 37 degrees off of the vertical. So it's okay that we've left the negative sign out because we're compensating for that by giving its direction as being 37 degrees away from the vertical. So now that we know the equation for the force due to gravity, we solve for it and find that it's 294 newtons. If you'll notice now, we've got in this right triangle, we've got the hypotenuse, which is the force due to gravity. We know its value is 294 newtons, and we know this angle is 37 degrees. That's the same angle as that angle there. So we can use SOHCAHTOA, the trig functions, to figure out the value for Fgy. Because Fgy is adjacent to this angle, we would use the cosine function, 294 newtons times the cosine of 37 degrees. In addition, notice that this is really important. We have a negative sign there. And the reason it's negative is that this vector is pointing downward. Similarly, for Fgx, we're going to use the sine function to figure out its value from SOHCAHTOA because it's the opposite side from the angle that we know. So we're going to calculate out 294 newtons times the sine of 37 degrees. And notice that this is going to be a positive value because it points to the right. So there are our values for Fgy and Fgx. Negative for Fgy because it points down. Positive for Fgx because it points to the right. So we simply take these values for Fgy and we plug it into our Newton's second law equations in the vertical. And likewise, we do the same for Newton's second law in the horizontal. We plug our values in, and then we find that the equations become these equations down here, where we plugged in our Fgx and our Fgy. Remember that our acceleration is 0 because this object is not moving. Its velocity is 0, therefore it's in static equilibrium. And because it's not moving at all, the acceleration is also going to be 0. So that makes ax and ay, both components of the acceleration, equal to 0. Anything times 0 is going to give us 0. So that makes these problems relatively easy to calculate. Very important that we put the same values in with the correct sign. So 177 newtons is positive, and in solving this equation, my static frictional force will become negative. Notice we have the correct sign, and we know that because our static frictional force is pointing to the left. For the normal force, we get a positive value of 235 newtons, and that's got to be correct as well because we notice that our normal force is pointing upward.